So in this video, I'm gonna be summarizing some main concepts on forces. I'll start by Newton's laws, which tell us some equations which give us relationships between the forces that can act on an object. Namely, I start with the first law, which we usually use when we want to study objects that are at rest or in a constant velocity. So once you see that your object isn't moving or it's moving in a constant speed, you immediately deduce that you have the situation where Newton's first law applies. And in that case, you can write an equation saying that F net is equal to 0. Remember, forces are vectors, so I'm gonna associate vector symbols to these. And this means we can't add the forces numerically, of course. The second case is the second law, which we use if the objects are in acceleration, and in that case, the forces are not balanced, they don't cancel out to 0. F net is not 0, rather it's equal to m times a. Again, I'm keeping vector notations for now. And finally, I have Newton's third law, which involves two objects which are interacting with each other. Newton's third law says that any object 1 exerting a force on object 2 will feel an equal but opposite force exerted by object 2 on it. In that particular case, you usually have two objects rather than one that you are studying in the problem. I can give an easy example. Earth and the moon, and these two are going to be interacting by gravitational forces. This is F Earth on the moon, whereas Earth is going to feel an equal but opposite force. This is F moon on Earth. The second law applies, for example, in the case of a free fall where the only force is the weight, and then W is equal to ma. We end up deducing that the acceleration is equal to gravity. And the first law can apply in cases where we have constant speed, such as a comet moving in outer space with no forces acting on it, or if we have a car that is moving on a frictionless surface. We can study, let's say, this puck on an air table. There's no friction, and then the only forces we have are the weight and the normal. Although we do have a constant speed, but the acceleration is equal to 0 because we don't have any horizontal forces. And then we say F net is equal to 0, W is equal to the normal in this case. So these are the three laws. I've given some simple examples, but in the cases where we have multiple forces and they're not really linear, we can't add things numerically because of the vector notation. So what we're gonna do instead is we're gonna be using x and y components. So for the first law, for instance, when I write F net is equal to 0, I'm gonna split that into x and y components for this equation. I'll write F net x equals 0 and F net y is equal to 0. And then I'm gonna check the x and y components for each force and plug them in the corresponding equation. How do we find the x and y components? This is the second section of this summary. So if we have two special cases. If the force is horizontal or along the x-axis, then its x component Fx is gonna be the force itself with a plus or minus depending on whether the force is along the positive x-axis that we choose or the negative x-axis, and its y component is gonna be 0. If the force is along the y-axis, so it's vertical or along the chosen y-axis, then I'm gonna say that Fx is 0 and Fy is going to be equal to the force itself with a positive sign if the force is along the positive y-axis, and I can write Fy to be minus F, the negative of the force itself, if the force is along the negative y-axis. Now these are the two special cases. We can take a simple example. If I have a box on a table and we're dragging this box with a rope, so there's a tension force, and in addition to that I have the weight force, the normal force, and maybe a friction force. So here the weight forces are vertical and they will be along the y-axis that I choose, and the friction is along the x-axis. To see things clearly, you can draw the x and y axes and represent the box by a point so that you can see the forces all starting from the origin. So I have a tension force. Let's assume the tension force is making an angle of 30 with the horizontal. And we have the friction force here, the weight, and the normal. So as you can see, W and N are along the y-axis. So their x component is 0, their y component will be plus or minus, depending on whether they are along the positive or negative of the y-axis. You can see how the normal is along the positive y-axis. You can see this over here. This is our axis. And thus we can deduce that this normal force is going to have a positive y component. So this is plus n. Its x component will be 0. For the weight force is along the negative of the y-axis. So it will be minus w. Its y component is negative. X component is 0, as we said before. And the friction force is a horizontal force. It's along the x-axis. So because it's a horizontal force, its x component is plus or minus f, and its y component is 0. So I'm going to say that fx is, well, fy is 0. Fx, let's take a look at where the friction is. It's in the negative part of the x-axis, so I'll put a minus sign. And finally, I have the non-special force, or the oblique force, which is neither along the x nor along the y-axis. It's our tension force here, with which we are pulling the box across the table. If the force is oblique, I'm going to be using some formulas. I'll write fx to be f cosine theta and fy to be f sine theta, where theta is the angle with respect to the x-axis. In our case, you can see how the tension makes an angle of 30 with respect to the x-axis. So I'll write the x component of this tension to be t cosine theta. So Tx is T cosine of 30. I'm going to check the sign according to where the tension force coincides on the x-axis. The tension, if we project it on the x-axis, it's on the positive side. This is the negative side of the x-axis. It's on the positive side. So it's going to be a positive component. The y component, T sine 30, remember, keep the same angle, which is with respect to the x-axis. Our formula contains theta, which is the angle with the x-axis, even for the y component. And let's project the y component on the y-axis. This is in the positive end of the y-axis. So the y component is also gonna be positive. We just found all of the x and y components. Once we find these x and y components, we can finally apply Newton's laws. So, as a matter of fact, as a summary for any force problem, what you should always be doing is you start with a diagram, as I have done here, represent the object by a point and draw the x and y axes. So this is our first step, draw the force diagram. Then we're gonna find the x and y components, as we have done here. And finally, I will use Newton's first or second law to solve the question. So in this case, let's assume that the box is in motion. So I'll apply Newton's second law. I'll write F net equals ma. And then I'll project along x and y. So I'll say F net x equals max, F net y equals may. And I'll just substitute all of the x and y components that I found here in these two equations. So namely, the x components are nx, which is 0, fx, which is minus f, and wx, which is 0. So I'll just substitute these. This will give me actually that I also have the tension, by the way, Tx, which is T cosine 30. So this will give me minus f plus T cosine 30 equals max. Let's assume that the box moves along the surface, so it's moving along the table, which means it's horizontal, so it has its x component equal to a itself, and its y component is equal to 0. For the y components, if you just add up all of the y components, we have the normal, which is n, the weight, which is minus w, no friction, and ty, which is t sine 30. you will get minus W plus N plus T sine 30 equals 0. We just got two equations, and we can use whichever one we find convenient to solve the question. It will depend on what you're asked to find, whether it's the friction, the acceleration, or the tension force. And that's typically the steps that you use for any problem which is on forces.